Welcome. One of the nice things about the Earth is that it has mountains, plains and deep oceans. It has a topography. We at Delft work in all these domains. Elevations can change over very short distances. In places like the Apuane Alps or Tuscany, peaks higher than 1500 meters are at few kilometers from the sea. Snow in the morning, afternoon on the beach. The diagram on the slide shows the percentage of the Earth's surface on the horizontal axis, which lies at a certain altitude indicated on the vertical axis. You can see that something like 30% of the Earth's surface lies at around 500 meters. An even larger portion of the Earth, nearly 50%, lies at around 4 kilometers beneath sea level. Why are only few regions very high and a lot of regions close to sea level? Topography is essentially controlled by isostasy. Isostasy is not much more than the law of floating bodies described by the Greek philosopher Archimedes more than 2000 years ago. Archimedes discovered that the weight of a floating body is equal to the weight of the displaced fluid. Here you see the mathematical formulation of Archimedes' law. Setting the weight of the floating body equal to that of the displaced fluid, you can extract h, which corresponds to its height of the top of the block above the fluid. In the real world, this would be the topography. As you can see, the only terms which are in the equation refer to the height of the block and the densities of the block and the displaced fluid. In other words, what happens below the base of the block is irrelevant. We define then a compensation depth, which is the surface separated domain with low changes from the one where no changes exist. An alternative formulation of the law of isostasy is that if isostatic equilibrium exists, then the weight of all columns above the compensation depth are the same. There are then three parameters controlling the topography of our block: the density of the block itself and of the displaced fluid, and the height of the block. In the upper part of the slide, you see that the higher the density of the floating block, the lower its topography. Indeed, heavy body tend to decrease in the topography. A decrease in thickness of the body produces the same result, namely a lower topography. Note also that the base of the thin block is higher than that of the thick block. But what does the floating block correspond to in the Earth? And the liquid? We answer this question looking back at the outer part of the Earth and searching for the part of the system which is more likely to behave as a fluid. Will this be the crust? Probably not. The lithospheric mantle? Surely not, as it is composed of very strong minerals. What about the asthenosphere? Yes, the asthenosphere is hot, has a small portion of melt, and can flow more easily than the overlying layers. Never forget that we are talking of flow at solid state, comparable to that of ice. The floating block is the lithosphere. The fluid is the asthenosphere. Let us look at the density of the floating block, the lithosphere, and of the displaced fluid, the asthenosphere. The simple fact that we are standing on the lithosphere implies that its average density is lower than that of the asthenosphere. But we know that the lithosphere is composed of two layers with very different densities. The crust is composed of low-density rocks and the lithospheric mantle made of heavy rocks. You can see representative values in the slide. The key observation is that the density of the crust is the lowest of all, and on the other side, the highest density is that of the lithospheric mantle. Like a piece of wood attached to steel, it is the crust which keeps the lithosphere afloat. Now let us go back to geology and consider a typical passive continental margin. Isostasy is able to explain most of the first order topography you see. Representative densities values are shown in the picture. On the left side of the picture, you have a thin, heavy crust underlain by a thin and heavy lithospheric mantle. No surprise that the top of this block will be very low, below sea level. On the right-hand side of the picture, on the contrary, you see that the lithosphere is composed of a thick, low-density layer overlaying the mantle. Obviously, this results in a very high topography, the mountains, and a deep root. Amazing how a simple relationship like the one proposed by Archimedes 2,000 years ago can explain the topography of the Earth.